then I advise you to buy it, to invest 400 dirhams, then you save for 1 or 2 or next semester you take, you save 12,000 dirhams a course. It's really useful. It's really useful because it has many problems that it gives you an opportunity to solve. You cannot, then it gives you another chance, third chance, can give you hints until you solve it correctly. There are a lot of resources, videos, problem solving videos, which are not available with the PDF file that you buy illegally from the net. PDF is not really useful. It is useful, but it's not as useful as that. So let's talk about rolling, and we know what rolling is. A motion of the center of mass and rolling about the center of mass. In the first part, we talked about rotation about a fixed axis. There's no motion. Rolling, we call it smooth rolling. If there's no skidding, does not skid, smooth rolling, and we have talked about it. As I said, I'll not talk much. This is an example from the book. See this skater, so the wheel is rotating and you are moving with the center of mass at the same speed, so you have 2 degrees of motion. So this is, it clarifies the idea what rolling means. It rolls and moves at the same time. But another figure which was interesting in the book also, which is the relation between the linear and the angular parameter. S equals R theta, V equals V center of mass omega R, which means all angular parameters for a rotating object are the same, but the linear parameters are the same. And that's clear in this picture here. This is a bicycle wheel. It's rolling without skidding because smooth rolling, as I said. And look at the spikes. The lower ones are very clear. The upper ones are blurred. Why? Because they're faster. You don't see the difference. So you see, because as you are away from, if they're rotating about the floor, for example, rotation about the floor. So these are the speed with the spike near the ground is 0. As it goes away, it becomes faster and faster because V equals omega R. As R gets larger, V gets larger, and the upper half, you'll see them better in the PowerPoint, not on the screen because of the projector, but you see them. They are still there, but they are not very clear. They are there because they are much faster than the ones lower. So this clarifies and let you always remember that V is not the same. It depends on the distance from the axis of rotation. So this is one thing.
Okay, but Professor, isn't the axis of rotation the center of mass?
Center of mass, yes.
So it should be the same speed on all sides?
No, just a minute. No. Now this is rotating about the ground, about what causes rotation, this friction.
Friction, yes.
Friction. So the friction causes rotation is rotating about that point here, this figure. Okay? Now, if you consider the center of mass, yes, about the center of mass, all these will be the same. All points will be the same, and we have seen it in the figure in the previous class. We talked about this one, okay? You see here, pure rotation about center of mass, V is the same, but if it's about this one, the last figure on the right hand, what is the here? See here, V's are the same as you said. But here about this one, you see the V is larger than V here. And V at the ground is 0. So the figure that you have seen is this one, the actual, okay? Not the center of mass. Okay, let's quit this and rolling with energy. We talked about the energy. It has 2 energy, rotational and translational. Okay, about the center of mass. And what causes the rotation is static friction, not kinetic friction. If there's kinetic friction, then it's not rolling. It's not smooth rolling. We wrote it smooth. Where is it? I wrote it. I'm sure. Yeah, smooth rolling. If there's no skidding, we call it smooth rolling. Okay. If there is a kinetic friction, then it's skidding, it's zinc. So it's not, we cannot do the same treatment. I put these to solve, we talked about energy, we solved several problems, at least 2 or 3. But let me also talk about how to calculate the acceleration of the center of mass. We did this example with energy. Let's start with the Newton's laws. So this is a rigid object, can be a sphere, can be a cylinder, can be a disc, can be anything. Rolling without skidding, it's a smooth rolling. And he took the positive axis to be to the right upwards, and it's moving down, which means that the center of mass is accelerating in this direction, and negative acceleration, isn't it? And the rolling is caused by Fs, static friction, which is in this direction. It causes a rotation in a counterclockwise, which is positive. linear acceleration of the center of mass is negative, it's down, because this is my positive axis going this way, it's accelerating down, but rotation is positive. So let's write the equations of motions in Newton's law for both translation and rotational motion. For translational motion, what force do we have? The positive is upwards, I'm saying. So I'm taking the positive up, so Fs, F static is upwards.
Is this coming in the exam today?
I don't know, I'll tell you in the evening after the exam. We did similar things. Minus the weight, what's the weight? You see this, the weight is mg, has an mg cosine perpendicular and mg sine parallel to the surface. So it's minus. I'm doing this because it's an example in the book. So we didn't do it in the previous, that's all. Because you may ask me, sir, do we have to memorize this formula, which we see in the 1 minute? Minus mg is equal to ma. Okay, ma center of mass, I know it's moving down, but when I solve I get negative. If you, because you know it's negative, you put minus here, then you get it positive. Okay, so I just put it in. What about rotation? What caused the rotation? We said about the center of mass. It's Fs, isn't it? Torque, sum of the torques equals I alpha, and the torque is Fs minus R is equal to I alpha. And what's alpha? But I put minus A over R. Why? Because alpha is positive, it's counterclockwise, and the center of mass is negative. If you combine these two equations, you'll find the center of mass, Cm. You'll find the center of mass, which is this equation. You see it's negative. Minus g sine theta divided by 1 plus I, this is the I about the center of mass, of course. We talked about the center of mass. Divide by mr squared. Now, if you have a sphere, then you put I for the sphere. If you have a cylinder, put for a cylinder. If you have a hole, it's for the. Yes?
The A, we put it negative because it's rolling down. We don't
Yes.
do our down motion. Okay.
Yeah, that's why we, sorry. Now, there's another example to the yo-yo. You know the yo-yo? That does it. So this is the yo-yo here. There's a thread tied in your finger, it comes down, it comes up. So what are the forces active in it? mg and the tension. So, what causes the rotation is the tension, T times R, isn't it? And what causes the acceleration down is mg. Sorry. So it's very similar. You have tension minus mg is equal to ma. Very similar to this equation. For the rotation, T times R equals I alpha. So the only difference, instead of mg sine theta in the resultant, we have mg here, isn't it? So for the acceleration,
عندي سؤال بس عن last one. Why is it Fs minus mg sin theta and not the opposite? mg sin theta
because
minus
he
theta.
said in the question, he chose positive x to be here, this direction.
He chose بس
Now, if you
isn't
choose
it-
it down, then everything, the answer will be positive, the same thing.
But
He
this
said, this is my positive x-axis, this is my positive y-axis. So I don't want to upset him and change my assumption. It's the same thing. And now if you say direction of motion is positive, you are right. Then you say mg sine theta minus.
Fs equal to ms.
Yeah. Okay, it's the same.
Professor, for the example, let's say they said find the kinetic energy. They had 1 over 2 mv squared and 1 over 2 I alpha squared because it's rolling.
I omega. Yeah, yeah, we did this example. So in this example, the yo-yo, instead of mg sine theta, we have mg. So the answer will be exactly the same. See, remember that equation? Go back again and come back. G sine theta minus G sine theta over 1 plus. Remember this. So only for the yo-yo, instead of G sine theta, we have G, because the force is mg always. So this is the formula for the acceleration. Now if you have a sphere, you put I equals 2 over 5 mr squared. If you have a disk, mr squared over 2. Okay, so this is just for completeness, because these two examples I didn't mention in the previous class. Okay. The last section, which is not section, so the last topic, it has 4 sections, 5, 6, 7, and 8. 11. This is about angular momentum. Distributed them, conservation of angular momentum, Newton's law, and so different sections, but it's all deal with angular momentum. Section 9 is not required, which is the gyroscope. Okay? Okay. See? Two shells. Okay. So, what's the angular momentum? By definition, L, although the book uses small l for point masses and L for rigid bodies, some textbooks use L for both, doesn't matter. L as angular momentum is defined as R crossed with P. What was the torque for rotation? R cross F. It's very similar. We have a linear momentum. R cross is defined as the angular momentum. So let's take an example. If you have ice rink and you have a pole fixed in the ice and you are skating or your sister is skating straight to the pole and offset a little bit from the pole, not directly, and very fast and holds the pole, what happens? She will rotate. That's the angular momentum. Because of the velocity and she has a distance from the pole, then rotate. But if she comes straight to the pole, she just hit the pole, she will not rotate, isn't it? So this is just a practical example. So L, as I said, he uses a small l here, R cross P. P is M, is a constant, which is scalar, R cross P. And you know cross product. It's extremely important, cross product. So you have the direction into account. So if R is parallel to V, then what will be the angular momentum? Zero. If it's they are parallel, it's zero. They are parallel, zero. They are perpendicular, it's up, okay? Okay. The units is kilogram meter square per second, because this is meter, this is meter per second. We just call it joule second. So it's the unit, it's kilogram meter square per second. It's called. It's very important to note that it's not necessarily that the object rotates about a certain axis about origin to have angular momentum. It may not rotate at all, it will have angular momentum. Let's take an example, which I mentioned in the morning. So let's say an aeroplane, Emirates, flying here, and I'm down, or let's say Air Arabia, because you're in Sharjah, exactly under that here, and let's say it's a 1 kilometer high. It's flying at 100 meters per second. And I'm here. What's the angular momentum of the airplane with respect to me? I'm looking straight at the airplane. A 1,000 kilograms, assume that it's 1,000 tons, but let's say 1,000 kilograms. Small helicopter. Okay? So what's the angular momentum? So this is R, direction of R, this is R, this is direction of P, isn't it? Direction of the velocity. It's flying horizontally. So this is the angle between R and P. So it's L is equal R M V sine 90.
So just one.
It's equal R M V.
Yes.
And you multiply them. Okay, that's not all. Let's say that it continued flying horizontally, not go up, not descend, for 10 kilometers more before starting ascending. So fly at the same height until it's here now. Now this is 10 kilometers, let's say. So this is 1 kilometer. So now it's here. Where's R? This is R. So it's R times V. This is the angle theta. Is that right? This is R direction, R hat, and this is V hat. You know, unit vector shows the direction. Hat. This is the angle between them. So what is the angle between them? R M V sine theta. What's sine theta? This is the opposite. It's this one. R sine theta is this one, isn't it? What's this? This is the initial one. It's the same as this. So the angular momentum depends on the vertical distance between them. So which means L is equal to R perpendicular times P. It's equal R perpendicular times MV, and the perpendicular distance not change. So until it reaches wherever Beirut, if it does not change the elevation, the angular momentum with respect to me is the same. If it changes height, that's different story. Okay? Or you can say R MV perpendicular. Okay? So this is the cross product. It's equal R perpendicular times P. It's equal R perpendicular times P. The magnitude. I'm talking about the magnitude. It's equal R P perpendicular, which equal MRV perpendicular, which is MRV sine theta, where theta is the angle between increasing R and increasing V. Please, yes, please.
Was it perpendicular is inclined, right?
Sorry, this is
Which
perpendicular
one?
distance. This is the perpendicular
I
distance.
forgot it was perpendicular once when it was inclined, right? It was like it's not horizontal, vertical, or perpendicular.
Look, I mean, perpendicular between the V and R. This is the R, and this is the V. Perpendicular distance between them is this one, always. VR sine theta, which is always the same.
So it'll be the same. It'll be the same in all points.
Yeah, all points.
Yeah, okay. Because
So
we
angle
take,
root will not change in this example.
we take R perpendicular, not R where
Yes.
the plane is.
Yes.
Okay.
So this is what I was saying. See, R P perpendicular, or R perpendicular times P, the same thing, which I wrote them here for.
Mm.
So this is the definition, and the unit is kilogram meter squared per second, or joule times second. Okay, Aisha? Angular momentum has meaning only with respect to a specific origin. You cannot say my angular momentum is this. No, with this, I said all the time I calculate with respect to medium. So it has to be with specific origin. It's not rotating about that origin, but we calculate it with respect to some origin. It is always perpendicular to the plane formed by the position and linear momentum vector. We said that many times in chapter 3. We said if you have C equals to A crossed with B, always C is perpendicular to the plane that has A and B. Same thing, you have L equals R equals B, so the angle is always perpendicular to the plane that has. From moving here, and the R from a certain point, the XY plane, then the angle should be either up or down, perpendicular to the XY plane. Yeah, this is, let me read it quickly. In part A, in the figure of the next slide, particle 1 and 2 are move around a point O in a circle of radii 2 and 4 meters. Here, so this is a circle, this one rotates, and this one rotates in this direction. Okay? Then it says, in part B, particles 3 and 4 travel along straight lines and perpendicular distances 4 and 2 meters from O. So this one, this is going this way, and this is going this way, the same distance from this approaching, this is going away from the origin. Okay? I did not remove the answers, I should have done that. All 5 particles have the same mass and the same constant speed. Rank the particles according to the magnitudes of their angular momentum upon point A, greatest first, which particles have negative angular momentum about it. Okay, so which one has the, don't look here, okay? You look? Okay. So you see, this is the distance, vertical distance is the same as this one. This is R, but I care about the perpendicular distance, which is the same. So this and this will have the same angular momentum magnitude. We're talking about direction, magnitude. Now this is a distance is 2, and this distance is more than 2, but the perpendicular is 2. So 4 and 2 have the same magnitude of angular momentum. What's the angular momentum number 5? Give you a hint?
0.
0.
0.
0, because the perpendicular distance
Is
is 0.
0.
Okay, is it clear?
I didn't get
See, 2 will go clockwise, so it's negative. He says which one is negative?
I didn't get 2 and 4.
1 and 3 are the same because R crossed with V. So they are moving this way, and this is R. The angle between them is 90 degrees. For this one, it's moving this way, and R cross with. So the perpendicular distance is R cross product gives you here. R perpendicular times V. The perpendicular is the same as this one. So they have the same magnitude. And for these two, this is the distance and this is the distance here, perpendicular distance. Not that distance is more, but I don't care about distance, I care about perpendicular distance. And you forget that, remember the example of the airplane here. As it goes straight, the angular momentum will not change. Newton's laws, let's see Newton's laws apply. We did this in the previous lecture. We started for a particle moving with velocity v. So the force is dp by dt. This is Newton's law for translation motion. Sum of the forces, assume there's only one force. And if you want to find the torque, then R cross F equals to the torque, R cross dP by dt, and because F is dP by dt, then you choose this, the chain rule, this dr by dt equals P plus R dP by dt. Okay? Then if you dr by dP cross with P is 0, why? What's dr by dt? What's the dr by dt? This change of distance with respect to velocity. But velocity is always parallel to v, isn't it? So this is 0. So we only left with the second term, which is R cross dP by dt is equal to the torque. Okay? So this is the derivative of that. So this is what R cross P is what? We define an angular momentum. So this is this is Newton's law in rotational motion, that sum of the torques is equal to dl by dt. dl by dt. If I want to rush towards the end of the class and I'll tell you if this is 0, if the torque is 0, what does it mean? If sum of the torque is 0. No change of angular momentum. Look at the equation. dl by dt is 0. What does it mean? What's L? Constant. L is conserved by momentum. We said if sum of the torques equals dP by dt, if this is equal to 0, right, the P is constant, and P initial is equal to P final. Isn't it? So of the system, collision, the two objects before collision, momentum is equal to the two objects after collision. Remember?
So it's the same.
The same thing. Total momentum is conserved if there's no external torque. If there's no external torque. We'll come back to that. See, this is still, it didn't say 0. This is in general. It's similar to the translation and conservation law. This is Newton's law. Both of them are forms for Newton's law for translation and for rotation. Okay. This is a particle, you see, R equals mv, R sine the angle phi between them, you see, increasing R and increasing V. This is the angle. Because in some other questions, he write cosine, and you say, sir, cross product is a sine. He does not use this phi, he uses this one. This is an angle between R and V, but they are not between decreasing, so he uses another. But by definition, increasing R and increasing V. So this is the angle that we should consider, sine phi. If R is parallel to V, L is equal to 0, we know that, we said that. If R is perpendicular, then V is equal to mv, which is this example.
So if they give us the other angle, what do we do? The angle between R and P.
You find the third one, the other one.
You find the other one?
Yeah, you can find it. You can use the other angle.
You can do 180
I
minus.
use cosine.
You can do 180 minus the other angle.
For a single particle, you use small l, and this is similar here. The torque and the angular momentum must be defined with respect to the same point, usually the origin for a single particle. The vector sum of all torques acting on the particle is equal to the time rate. Is translating this into words, time rate of change in angular momentum. Okay, and the same thing for this. This is an example. Again, the answers are there. This is a point mass here at a distance r from the origin, and there are 4 forces acting. Which one has a 0 torque? The one parallel or anti-parallel, isn't it?
Yes.
2 and 4. Which one is higher, 3 or 1?
3.
The same magnitude, 3, because they are the same forces, he says. Yeah, according to the magnitude, the rate. 4 choices of direction. Well,
The
3.
angle of F1.
The angle is more and magnitude is more, so 3 is more. Okay? Now, rigid body. Let's talk about one point. Now, a rigid body consists of infinitesimally many small particles. So add them up and integrate. Although your book still writes summation, and he does not like to see dm, use delta m. Add 0.1, 0.2 until infinity, which is the same as integration, took integration, all of them. Okay. So this is for a system particle, forget what it is. So L total is equal L for the first, the second, you have 1,010,000 particles, let's say this one. You add up all the angular moment as vector, you have vector addition. The rate of change, this then we call it chemical L. dl by dt is sum of the torques, external torques acting on the object. sum of the external forces. Still the same equation that acts for the single particle. Okay, net torque. So if the net torque is zero, معناتها L is constant of motion. The net external torque acting on the system of a particle is equal to the time rate of change of the system's total angular momentum. That's what we say. And if torque is equal to zero, معناتها dL by dt is equal to zero, يعني L is equal to constant. L does not change. Okay, L does not change. Now he used that how to add L around the z-axis, the perpendicular axis. It's sum of L's, and you know L is I omega. We'll see that. So M V for each one of them, but they are continuously connected. Instead of M equals dm times V, okay, VMR. So you have R perpendicular is equal to omega R, V perpendicular is omega R. So this will be equal to this equation. What's this here between the brackets? In the quiz, what you have, moment relation for a particle, mr squared. Now instead of m, you have delta m. So this is I, isn't it? This is I for the whole object. So L for that is equal to I omega for the rigid body. I omega, where omega is the angular speed, L is the angular momentum. So look at this table, compares rotational with translational motion, translational rotation. You have the force corresponding quantity of the rotation is the torque, R plus linear momentum, you have angular momentum. Linear momentum for a particle, linear momentum for a rigid body summation, which is angular momentum for a rigid body, L capital summation. Okay, linear momentum, okay, so F dV by dt, we have torque dL by dt. So conservation law, we have P was constant, momentum for any collision, for any explosion. And here we have conservation law, L is equal to constant when the torque is equal to zero, when the sum of the torque is equal to zero. So let's look at this question again. This is a disk, a hoop, and a sphere. What's the moment of inertia for the sphere? 2 over 5 mr squared. What's for this disk? Mr squared over 2.
It will be given, right?
It will be given. And this is mr squared. So which one is larger is this? And then this, and this is the smallest. Okay? So let's read the question. A disk, a hoop, and a solid sphere are made to spin about a fixed central axis by means of a string grabbed about them, with a string producing the same constant tangential force. All three objects. The three objects have the same mass and radius, and they are initially stationary. Rank the objects according to their angular momentum about their central axis. So it applies the same force, same distance. Okay, the angular speed will be the same, which means angular momentum R cross F. Sorry, R and F angular is equal to R cross P, sorry. F is the same mass, and the V is the same also. R cross V will be the same, R cross P is the same. So they have same. Which one, their angular speed greatest? So the angular momentum is constant, I omega is constant, L is equal to I omega. So if one of them has higher I, what will be the omega? Is lower. So the one with the smallest moment of inertia will have the highest angular speed. Is that right? Which one with the smaller angular moment of inertia is 2 over 5 will have highest angular speed. Then this one, because half, and this is full mr squared. Okay, so this is the answer. Conservation of angular momentum, I already talked about that. When you have sum of the torques equal to zero, then angular momentum is conserved. When there's no net external torque acting on the system along the specific axis, we apply conservation of angular momentum to relate initial and angular momentum about that axis. Yani L is constant. If this is zero, then L is constant, and L initial is equal to L final. This is conservation law. Okay, what's L? We divide I omega, and I initial omega initial equals I final omega final. It's conserved when, if and only if external torques are zero. Okay? So you can talk about this example. Please, we'll talk about this example when you jump from a platform to diving. So you change and your angular momentum by you start straight and then you tuck yourself your legs and then you start rotating with a different angular momentum. We'll talk about that. So it says this is a beetle and so the same one not for the beetle. The beetle rides from the rim of a small disc that rotates like a merry-go-round. Disc rotates. It's a beetle here at the rim. She starts walking. The beetle crawls towards the center of the disc. Do the following each relative to the center. Increase, decrease, or remain the same for the beetle's disc. Rotational inertia. Didn't understand the question, of course, you cannot answer. So there's a disc here, rotating about the axis, and there's a small object that's moving. Small insect, small man walking, anything. Now when it moves further, what happens to the moment of inertia? Moment of inertia initial is equal to moment of inertia of the disk, I for the disk, okay, plus I for the beetle. Isn't it? I by the beetle is equals to I disk plus F R squared plus. This is R. Okay, mr squared. So this becomes here, what happens to mr squared? Becomes this. So moment of inertia decrease. If moment of inertia decrease, I1 omega 1 equals I2 omega 2. If this is constant, if this decrease, what happens to this one? Okay, so this says, as close, what happens to the following? Moment of inertia will decrease. We said R becomes this, isn't it? Moment of inertia will decrease. What else is B? Angular momentum will be the same, but what is the angular speed will decrease as we showed here. If this is sorry, what's that? Will increase, yeah. Will increase because angular momentum, angular speed will decrease. We'll solve the same question, but not with a B. With Abdelaziz standing on a merry-go-round. We come back to this, don't worry. We go back to that example, I added that last night. Go. Yeah, this is the example. This is a merry-go-round like lap. So it says horizontal platform, shape of a disc, circular disc, rotates freely on the horizontal plane. It rotates like this. And there's a student standing on the rim, at the edge. Okay? The platform has a mass capital M and 100 kilogram and a radius of 2 meters. A student whose mass is 60 kilograms, okay, walks slowly from the rim towards the center. If the angular speed of the system is 2 radians per second when the student was here, it was rotating, what will be the angular speed when he reaches half a meter from the center?
To decrease. Right.
It will increase. Let's see how much. So you have to apply angular conservation of angular momentum. Yes.
You know إحنا عندنا في conservative energy وفي عندنا مثل الأحوال بدون conservation of energy هون في عندنا without conservation of momentum ولا is it always conserved?
No, energy is not always conserved. We'll see that for this example, energy is not conserved. Energy is not conserved because he's putting some muscles, some energy to the system. Only angular momentum is conserved here. I'll talk about it in a moment. So we have sum of the torques external is equal to 0 because this is one system. The student and the platform is one system. There's nothing. Now, then L initial is equal to L final. Angular momentum is conserved. This means dL by dt for the system is equal to 0. Yani L for the system is the same. Does not change. What's L? I initial, omega initial should be equal to I final, omega final. Now let's calculate what's I initial. I for the disk about the center of mass, which is m r squared over 2. I center of mass for the disk is equal to mr squared over 2. Plus I for Abdelaziz, what is it? R squared. R is the same. Okay, it was at the edge. Okay, what's I final? Still that disk is rotating in the rotating plus m sine 0.5 squared. This r is equal to 2 meters. This r is 0.5. Okay? M is 60 kilogram. This is 100 kilogram.
So I final will be less than.
So I final will be this. Omega initial is known. Then omega final is equal to I initial. Omega initial divided by I final.
And we found m r squared by parallel axis here.
I final. No,
No, because it's at the edge.
it's moving. No. It's a point mass. Rotating about the
Because
center.
there's a point mass and there's another.
Well, that disk is rotating about its center of mass. So it's I center of mass.
And there's also a point.
That point or that person, we assume it's a point mass.
That's all, yeah.
Rotating it's mr squared.
Parallel.
No, not parallax, it's another object. So omega final divided by a small number to be larger. It will move faster.
Can we say 2 multiplied by 0.25? Oh, no. Divided by.
Yes.